Hello student, I am Dr.A.K. Professor of Chemistry. Today I am going to discuss chemical equilibrium. Just like in physical process we have discussed physical process, there is this equilibrium in physical process. Same way here is a equilibrium in chemical process. Same way. Okay, analogous to the physical system means like analogous to the physical system, chemical reaction also attain a state of equilibrium. These reactions can occur both in forward and backward directions. When the rate of the forward and reverse reactions become equal to the concentration of the reactants and the products remain constant. Okay, same way here also that reactions attain the equilibrium. When it will attain the equilibrium, that you listen, these reactions means chemical reaction. These reactions can occur both in forward and backward direction, in both direction. When the rate of the forward and reverse reaction become equal to the concentration of reactants and the concentration of product, okay, that situation is called chemical equilibrium. Means at chemical equilibrium, concentration of reactants and the products remain constant. Okay, this is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of forward reaction in which the reactants give products and reverse reaction in which the products give the original reactants. General example, you can understand that suppose A plus B are the reactants and it is giving the product C plus D. Okay, then this how will you understand this equilibrium? Then that I am telling you how by graph you can understand, by plot you can understand, means concentration versus time. Here what will happen, that first you understand that A and B means A plus B, that with the time what will happen of A and B, means concentration of A and B. Actually concentration of A and B with time, actually time is on x-axis and concentration is on y-axis. Then with time A plus B means concentration of A and B will begin to decrease. Okay, it will begin to decrease, and after that it will become, when both will react, then it will become just like a constant. Okay, and it will form C plus D. Okay, means concentration of reactant will decrease slowly, and after that product will begin to form. Product means C plus D will begin to form. Then first in the graph you should understand how A and B is decreasing. Concentration of A and B will decrease. Just it will look like a curve. Okay, one curve, but it is in decreasing form. It is decreasing. One curve means will be there. Then that you can see concentration of A and B is decreasing with time. Okay, with time, just like a curve, it will show just like a curve. Okay, and when A plus B will react, then after the reaction, when reaction is complete, then their concentration will not change. Okay, now just think for the product. Then in the beginning product was 0. In the beginning product was 0. As soon as A plus will react and will give product, it will begin to form product. Then with the time concentration of product will increase slowly and slowly. It will increase, means in graph you will find up. This is also a curve, but in upper direction, that slowly and slowly product is forming. With the passage of time, quantity of product will increase, and after that, when you can say their reactant, means A plus B completely reacted, like that way here product, when it will, after the reaction A plus B, it will form product, and that time again you will find that it became a constant, means reactant curve is towards down in the form of curve, and product it is also curve but up direction. It will increase, means reactant concentration will decrease and product concentration will increase with time. Okay, this I have told in a general way, general reaction. Okay, and both curve will cut in one place, because reactant which is coming down, it was coming down in the curve form and became constant. Like that way product is slowly and slowly it will increase, and after that become constant. Then both curve will cut one place. Okay, then when they become constant, in both cases becoming constant, then that constant condition is for equilibrium. Okay, and also the two reactions occur at the same rate. Okay, same rate, and the system reaches a state of equilibrium, means formation of rate of formation, that is the, and here reactants are decreasing, then that rate at which both reactants are reacting, that rate and the rate at which product is forming, both are same. Okay, at equilibrium position both rate of forward reaction, means formation of product, and from the product again it will give back reactant, then that is called reverse reaction. Then rate of forward reaction becomes equal to the rate of reverse reaction or backward reaction. Okay, then this happens, both rate will be same. When will be the same? Then at equilibrium. Rate of forward reaction is equal to the rate of backward reaction or reverse reaction. Okay, now similarly the reaction can reach the state of equilibrium even if we start with, means from the C plus D also we can get, from C plus D means from the product you can get A plus B, and from the A plus B you will get C plus D. From the both end equilibrium can be attained. Okay, equilibrium can be reached from both end. Okay, either direction, from the reactant side as well as from product side. The dynamic nature of chemical equilibrium can be demonstrated. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber process. Okay, This question is also asked. Ammonia is produced by Haber process. And what I have told now, all things are proved in the case of production of ammonia by Haber process. In a series of experiments, Haber started, means scientist. Okay, Haber is the name of scientist. Then Haber started with known amount of dinitrogen, means N2, and dihydrogen, means H2, maintained at high temperature and high pressure. This is the condition. Nitrogen and hydrogen both should be at high temperature and high pressure. Okay, and then at a regular interval, you can say determined the amount of ammonia present, that how much ammonia is giving at a certain interval, regular interval. He determined the amount of ammonia produced. He was successful in determining also the concentration of unreacted dinitrogen and dihydrogen, means how much it is remaining, that also concentration he has obtained. Okay, he was also successful in determining also the concentration of unreacted hydrogen and nitrogen. Okay, this has been done by Haber. Okay, and this actually I will send one plot. By that plot you can understand also. Okay, plot shows that after a certain time the composition of the mixture remains the same, even though some of the reactants are still present. Reactant may be present, all will not react quickly, but whatever reacted they are maintaining equilibrium. Okay, this constancy in composition indicates that the reaction has reached equilibrium. Okay, in order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting condition for partial pressure and temperature. But you can say so many methods are there to see the equilibrium. Then ammonia is the best example. Formation of ammonia from nitrogen and hydrogen at high temperature and pressure. Okay, this I have told you about the formation of ammonia by Haber process. Okay, question is asked. Now I am telling you just like you can say physical equilibrium. Here chemical equilibrium also you can define. Both definitions are same, 99.9% same. Only that is for physical, there was no chemical change, only physical change. Physical change means that only transition is going on. You have seen ice and water. Ice is melting and water is forming. Physical change. Okay. Candle, burning up this candle, you leave it, any melting things. And like water also, ice and water. Ice is converting to water, water is converting into, means liquid is converting into the vapor. Only physical change is there. Chemical formula is same, H2O. Okay, when chemical formula will be changed, same, only transition will be there from one state to the other. That type of reaction is called physical reaction. Chemical reaction, that now new things will be formed. They will not have the same chemical formula. Product will be different for chemical formula than a reactant. That is a different between physical change and chemical change. In chemical change, A plus B is there, they are making a new compound, C plus D. New product they are getting, and their chemical formula is different. You can't represent by the same formula. That is the different. And now I am telling about the these things, chemical equilibrium. Chemical reaction reach a state of dynamic equilibrium in which the rate of forward and reverse reactions are equal and there is no net change in composition. At equilibrium, there is no net change in composition. This is the definition of chemical equilibrium. Again, you listen. Chemical reaction reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in composition. Then some example I am telling you. First common example I told you that nitrogen gas and hydrogen gas means N2 plus 3H2 both are gas and it is forming 2NH3 ammonia gas. All three are gas. Homogeneous, you can tell this reaction is also called homogeneous. When all are in the same phase, reactant and products, when both are in the same phase, then it is called homogeneous reaction. Homogeneous. Okay. And when reactant and products are at a different phase, then that is called heterogeneous reaction. Then here I am talking about the homogeneous reaction, means nitrogen is a gas plus 3H2 means hydrogen, 3 mole of hydrogen, 1 mole of nitrogen, 3 mole of hydrogen, both are gas. Now what it is giving? Then it is giving a product 2NH3 means 2 mole of ammonia. Always remember, okay, N2 plus 3H2 is equal to 2NH3 means sign of equilibrium. 2NH3, NH3 is also gas. Okay. Then here again at equilibrium same type of graph it will form. One curve will be just like a down, one curve in down, other curve in up direction. Okay. Then first example I told you N2 plus 3H2. Okay. Then both is possible. Synthesis, that is the formation, synthesis of ammonia I told you, and decomposition also, decomposition of ammonia. Now ammonia is there, when it will decompose, then it will give N2 plus 3H2 means 2NH3, it will give N2 plus 3H2, 1:3 ratio. Always remember 1:3 ratio. 1 mole of nitrogen plus 3 mole of hydrogen, it will give 2 mole of ammonia. Then during the decomposition reverse case means 2 mole of ammonia will give 1 mole of nitrogen and 3 mole of hydrogen. Then reverse reaction you can write in a reverse way, means 2NH3 is equal to N2 plus 3H2. But here in the place of equal you write sign of equilibrium. Always in equilibrium chapter or wherever you want to tell equilibrium, don't write equal, you write sign of equilibrium, means double half arrow. Okay. Second example I am telling you, that is the formation of or synthesis of hydrogen iodide, HI, hydrogen iodide. Then how will it form? Then H2 plus I2 means 1 mole of H2, 1 mole of I2, it will give 2 mole of HI. 2 mole of HI means I2 plus H2 sign of equilibrium, it will give 2HI means 2 mole of HI. Again Reverse case also you can write decomposition means 2HI will give 1 mole of H2 plus 1 mole of I2. Okay, reverse way. Then now I have given 2 example. Then there if you will plot you want to see, then I will send the plot. Then you will find always concentration versus equilibrium. 2 graphs are there. First graph I told you concentration versus time. Now what I am telling you, that is the synthesis or decomposition in both cases, either of synthesis of ammonia or synthesis of hydrogen. Same nature you will get. Then here plot will be concentration versus equilibrium. Concentration versus equilibrium. Equilibrium with time. Equilibrium with time means formation time or decomposition time with time. This is also concentration versus time. Then here we are talking about the equilibrium, how equilibrium is changing with the time, how you are getting equilibrium with the time, either in case of synthesis or in case of decomposition. Okay, just reverse of synthesis, you will get that diagram for decomposition. Okay, this I have told you about the, I can say, this chemical equilibrium. Okay, 2 example I have given you, synthesis of ammonia and decomposition of ammonia. And second example, synthesis of hydrogen iodide means HI and decomposition of HI. Okay, then total 4, 2 to each, 4. Now I am going to discuss law of chemical equilibrium and equilibrium constant. Okay, then here what I have told you, that things in details you cannot tell me. Thus I am telling you details of only all these things. One you will understand, for one reaction, if you will understand same reaction, for all reactions same things, 99% will be the same, minor change I will tell you. Same process means you will get equilibrium constant in the same way for any reaction. 5, 6 are common, I will tell you. Okay, and only in that you will understand law of chemical equilibrium. Law of chemical equilibrium, actually in a simple way I am telling you with a common example. Okay, suppose A plus B is reacting, means these two are reactant and they are giving C plus D product. 2 reactants are giving, suppose 2 products. Okay, 1 product also they can give, 3 product also they can give, 4 product also they can give, but just for a easy understanding you consider 2. Reactant may be 2 also, 3 also, product may be 2 also, 3 also, 1 also. Okay, but for a better understanding, you consider A plus B is reacting and it is giving 2 product C plus D. Correct? In the middle you write, don't write equal sign, you write equilibrium sign. Means A plus B sign of equilibrium and it is giving C plus D. Now here you understand, concentration is represented by big bracket. In big bracket, suppose A is there, then that means that is called molar concentration of A. It is read like that, molar concentration of A in big bracket, 2 bracket or big bracket. Under that you have written A, then you can read as a molar concentration of A. Same way, if B you are writing in the big bracket, then molar concentration of B. And C you are writing in a big bracket, under big bracket, then molar concentration of C. Same way, molar concentration of D. Big bracket means, big bracket represents the molar concentration. Okay. Then now, what believe that you can say chemical equilibrium here, equilibrium, uh, that is for this equilibrium reaction, what I told you, A plus B, and sign of equilibrium C plus D. For that, for this equilibrium, for this reaction, what is the equilibrium constant? The equilibrium constant is very easy to read. Actually, one scientist is there, his name is Guldberg, 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 and Peter Waage, 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 proposed in 1864 that the concentration in an equilibrium mixture already you know that at equilibrium position, what is the, you can say, reactant and concentration of product mixing together is called equilibrium mixture. Okay, then these two scientists, that is the Guldberg and Peter Waage, proposed in 1864 that the concentration in equilibrium mixtures are related by the, you can say, following equation, that is the following equilibrium equation. What is that equation? That is also called that is the K, equilibrium constant. K, capital K, that is equilibrium constant. K is equal to what? Then very easy, concentration of products divided by concentration of reactants, that is equal to K. That K is equal to, K is called equilibrium constant. And one more thing, that suppose I told you A plus B is reacting, then how many moles of A is there? Then suppose a small A plus B is capital A plus capital B, capital C plus capital D. But now how many mole reacted? Then suppose capital A, capital A means reactant A has a small a mole, means 1 mole, 2 mole, 3 mole. Then general way you write a small a. Like that way, how many moles of B was there? Then a small b. How many products he has given? C. C, how many moles? Then suppose you got a small c. And D got a small d. Means C product got how many moles? C mole. And D product you got a small d. Then now when you are writing the K, equilibrium constant, then K is equal to, I told you that products of concentration means C into D. Concentration of molar concentration of C into molar concentration of D divided by molar concentration of A into molar concentration of B. But now power you have to write according to the coefficient. Coefficient of capital A, coefficient of capital B, coefficient of capital C, coefficient of capital D. Means C and D you have written. Then C power C, D power D. A power down, A power A, B power B. Then now suppose you have only 2 reactant and 2 product. Suppose there were 3 reactant and 3 product. Then like that way you have to write upside 3 and down also 3. Then that's why you don't know how many reactant, how many products are there. Then dot 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 you can write upside also, down also, dot dot dot. Maybe more than 2 reactant, maybe more than 2 product. Okay, then this K I have told you that is actually equilibrium constant. Here K is means K is equal to, you can write K generally it is written as a Kc. Kc, C means concentration. Okay, C means concentration. Then equilibrium constant. Equilibrium constant is generally denoted by Kc, a small c. K you write and a small you write a small c, Kc. Then Kc is equal to molar concentration of C into molar concentration of D divided by molar concentration of A into B, molar concentration of B, that is the Kc, where Kc is the equilibrium constant, and the expression on the right side is called the equilibrium constant expression. This is a general expression I told you. Equilibrium constant expression means C into D divided by A into B. Power also you have to write C power C, D power D, A power A, B power B. Okay, then this is called equilibrium constant expression. In examination, in written examination, they will ask to derive. Then this is the general expression I told you, and individual only the same way you can derive for any reaction, no problem. Just I am giving example. Suppose you can say H2 plus I2, H2 gaseous and I2 also in a gaseous form, and it is giving 2HI. 2HI means 1 mole H2. H2 has nothing is written. H2 plus I2, that is equal to 2HI. 2HI, 1:1. 1 mole of H2, 1 mole of I2, it is giving 2 mole of HI. Then now 1 mole H2, 1 mole I2, 2 mole HI. Then how will you write expression Kc for this reaction? A very simple way. Kc is equal to what? HI mole, HI in bracket you can write, big bracket, power 2 divided by molar concentration of H2, means H2 in big bracket into I2 in big bracket, means HI power 2 molar, HI molar concentration you have written in big bracket HI power 2 down, means divided by molar concentration of H2 into molar concentration of I2, that is equal to Kc. Very easy way, quickly in a second you can write. Same way, but here you have to understand, already I told you, molar concentration at equilibrium, molar concentration of H2, that is equal to molar concentration of I2. Both are same. It is evident from what I discussed from that way, that number of moles of H2, that is equal to number of moles of iodine. Okay, that is related to the half of number of moles of HI. Okay, because 2HI is given, 1 mole they are giving 2 mole, then half mole they will give 1 mole. Okay, this you don't forget. Then now I have told about the expression of, you can say H2 plus I2, that is equal to 2HI, means sign of equilibrium 2HI, then Kc value I have told you. Okay, same way you can write for any other reaction. As for example, you can write these things, decomposition. Okay, just I have told you for the formation, means synthesis. Now if you will think for reverse reaction, means HI, 2HI is giving H2 plus I2, then expression will be reverse, means molar concentration of H2 into molar concentration of I2 divided by molar concentration of HI power 2. Okay, then now reverse reaction. In first case actually it was Kc, then now in second case it is a reverse of first, means 1 upon Kc. 1 upon Kc. Okay, what was the formation? Means synthesis. For the decomposition, reverse case, it will be 1 upon Kc. Don't forget this concept. Decomposition means whatever you got for the synthesis, just 1 upon, because you are reversing, you are getting reverse, means down is going up, up is going down, then obviously Kc will become 1 upon Kc. Okay, means Kc inverse also you can write. This you don't forget. Okay, Then I told you about the in case of synthesis and decomposition. At a given temperature, the product of concentrations of reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the products of concentration of reactions raised to their individual stoichiometric coefficient has a constant value. Okay, whatever value will be, that will be constant. Stoichiometric means coefficient you are talking about, 1 mole, a small b, a small c, a small d, that is called stoichiometric, means coefficient. Okay, then now just to understand again, at a given temperature, the product of concentration of products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentration of reactants raised to their individual stoichiometric coefficient has a constant value. Value is fixed. Okay, this is known as equilibrium law. This is called equilibrium law or law of chemical equilibrium. That is the Kc, na? What we are telling Kc or 1 upon Kc in the reverse case, in the case of decomposition. Then this Kc value is fixed, constant. This Kc is called actually a law of chemical equilibrium, also known as equilibrium law. Okay. Then now already I have told you one more example I want to tell you. Okay, but exact Kc value, right, for A plus a small means A plus B is giving C plus D. A small a, number of moles of number of moles of A is a small a, number of moles of B is a small b, number of moles of a small c, and number of moles of D is a small d. Then finally you write case in the case of synthesis, Kc is equal to C to the power C, D to the power D divided by A to the power A and B to the power B. Also in molar constant in bracket you have to write. Don't forget. Then this expression you have to write. This actually its value is constant. Then that Kc, this expression actually is called equilibrium law or law of chemical equilibrium, because it has a at equilibrium, that they will get at equilibrium and that value will be constant. One more example I am giving you, that is uncommon example. Okay. Then now suppose it is a 4NH3 plus 5O2, 4 mole of ammonia, 5 mole of oxygen. It is giving 4 mole of NO, means nitric oxide, and 6 mole of water, vapor form, means gaseous form. Then for this you can write the Kc value very easily. First product you write, then 4NO plus 6H2O is there. Then NO power 4 and H2O power 6 divided by reactant was 4NH3 plus 5O2, means NH3 power 4 and oxygen power 5. Okay. Then all things have to write in a big bracket. Then molar concentration of different species is indicated by enclosing these in a square bracket or big bracket. And what I told you now, like that way. It is actually this bracket implied that these are equilibrium concentration, not only molar concentration. Molar concentration may be for reactant, may be for product, but here in a Kc, when you have written Kc expression, then that time it will be called equilibrium concentration. Okay, same molar concentration, now it will be called equilibrium concentration. Okay, while writing expression for equilibrium constant. Kc is equilibrium constant. Then you are writing that time this molar concentration is called equilibrium concentration. General way you can tell molar concentration, but at equilibrium, what is the concentration? That is called equilibrium concentration. Okay. Then I have discussed all the things, and also I told you that what is for synthesis. In the case of decomposition, it will be reversed. That is equal to, suppose for the synthesis it was a Kc. For the synthesis it was Kc you have written, and for the decomposition again you will write, you will get Kc. Suppose that is the K dash C, K dash. Okay, during synthesis you have written Kc. Then for the for the decomposition, same way you will write. That time you can write K dash C. K dash C is equal to expression, whatever you have, according to the equation you can write. Then how both are related, Kc and K dash C? Then inverse way. Inverse way means K dash C. K dash C is equal to 1 upon Kc. That is the relation. 2 marks question. You will derive Kc value in both cases same way. But how both are related? Then synthesis and decomposition both are related. Decomposition is related to inverse of synthesis. Decomposition means K dash C. As for example, K dash C, that is equal to 1 upon Kc. Reverse of synthesis. Decomposition equilibrium constant value will be inverse. You can write in the same way, but how they are related? Just reverse. Okay, suppose Kc value was 2, then decomposition value will be 1 upon 2. If it is 3 for synthesis, then decomposition will be 1 upon 3. Reverse case, suppose it was 3.107 into 10 to the power 5, then K dash C value will be reverse, 1 upon this value. Okay, means 3 into whatever I told you, that value. Reverse. Don't forget, 2 marks question is asked. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. Means forward direction and backward direction. Rate of equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. Now for every reaction, same formula you can use. Same thing, same expression, same way. Okay. Already I have told you these things. One more thing before going ahead. Suppose this example, decomposition of synthesis. Suppose in the reaction you have written H2 plus I2, that is equal to 2Hi. Okay, 1 mole H2, 1 mole I2, that it is giving 2 mole of Hi. Okay, if you want only 1 mole Hi, then if you want only 1 mole Hi, then half mole both are required. Half mole H2, half mole I2 is required. Okay. Then now for this you can write the expression same way. If half mole is giving 1 mole, then same way Hi, molar concentration of Hi divided by molar concentration of H2 power half, and into molar concentration of iodine power half. Okay, this is the you can say way to write the expression. Okay. Now suppose you want to write you can say general way, NH2 plus NI2, NH2 plus NI2. Suppose it is giving 2N HI. In general way, N you have written H2 plus I2 is equal to 2HI. That you know, only N you have to write in the beginning. That's enough. Then N into H2 plus N into I2 all are in gas, that is equal to 2 into NHI gas. Then like that way expression you can write. That will come Kc value you can write in the power n, because n just like Kc value in the case of here written half H2 plus half I2, that is the HI. Then HI divided by H2 power half and I2 power half. Then Kc value you can write like that. Kc will be half. Kc and upside you can write half. Okay. Then like that way here you can write Kc power n. Kc power n. What is the number of moles? What is the number of moles? That will go to the power of K. Kc power n. Okay. This you should remember always. Now I have discussed I can say general way, and with one example HI, and also I have told you about the homogeneous equation and heterogeneous equation. Homogeneous equation I told you, in a homogeneous system all the reactant and products are in the same phase. Example I told you, nitrogen gas plus N2 plus 3H2, it is giving 2NH3. All are a gaseous form, reactant and products. This is the example of homogeneous equilibrium. Okay. And now these things, one expression is there and a relation is also there between Kp and Kc, that I will discuss in the next class. Okay. And now I am stopping only here. Next class also I will discuss numericals. Thank you.